What I'm going to show you is what I did, which is part of the development of the mechanical engineering program, because I've been here for 36 years. And what I've been doing is part of what the mechanical engineering department has been doing, really. So since July 2020, I've been the director of the graduate program. And just very quickly, I worked for the Navy from 1994 until 2018. I was a summer fellow in Pennsylvania, and then I was a consultant in Pax River, Maryland. And then I became a distinguished summer faculty fellow at Port Hueneme in Oxnard. So I worked for the Navy for many, many years. And my work involved aircraft, landing gears, the fuselage and the engines and the coatings and especially corrosion. We worked a lot on it. And I received from the National Science Foundation and the Navy and NASA grants for over $3.2 million. And I consulted for many companies like Boeing and Northrop and Aerospace Corporation for all during these years. And like some of the equipment that we have, which I think not many universities in the world has, is a hydrogen annealing assembly. This furnace can go until 2000 degrees centigrade, not Fahrenheit, centigrade. And we use it for annealing rhenium, which is used in rocket nozzles, and any of the expensive refractory metals which need a reducing atmosphere. So this item is not present at other universities. It might be present in industry, like industry of rhenium or other industries with high temperature applications. But I got this from the NSF, National Science Foundation, and it's a very important piece of equipment. This is another view of it. This is the hydrogen furnace, and these are hoods and connections. Actually, there is a small building beside the tin shed area, beside our design center, just was built to operate this furnace. Other machines I got from the National Science Foundation, if you came and worked with us, you hopefully will work on it, is a fracture mechanics system. We can do here fracture toughness, high cycle fatigue, low cycle fatigue, fatigue crack propagation, stress corrosion. It's a very important machine, and we did lots of work on it, but we can still do much more work. I published with the graduates and the undergraduates over 200 referee journal and conference proceeding publications. I did supervise over 50 MS theses in these years, and every thesis was published in a journal, except one which was published in a conference proceedings, which was refereed as well. I delivered also several keynote speeches and plenary lectures in international conferences. For example, this is a conference which has to do with mechanical and materials engineering. It was in 2018 in Korea. This is me. I was the chair of the conference. This gentleman is from UC Berkeley, and this gentleman is from Taiwan. This gentleman is from Korea, and this gentleman is from Japan. So this is one of the conferences I went into. This was my keynote lecture. Then we went in 2019 to Japan. And you see one of the people in the old picture, this was mostly Japanese professors. And this is one of the sessions that I chaired and with the people who spoke in the session. And my research interest now is characterizing additive manufacturing materials and processes. And in general, metallic processing, modeling, experimental techniques, and failure analysis is something which I work with my students on. Like I said, I supervised over 50 theses. I have to go and make a count. I didn't want to say a certain number, but I know there are over 50. And like I said, every thesis was published in a referee journal with the student's name as the first name. And usually we have undergraduates helping every graduate, and they come as co-authors after that, and my name is last. And all the theses we had were good because they were accepted for publication. Excuse me. This is one of the machines we got from the National Science Foundation. It's called Universal Testing Instron 4505. It's universal because here we're doing tension. If you remove the grips, you do compression, you do 3-point bending, you do 4-point bending. So that's why we call it as universal. This is another machine called Tinius-Olson. We use it for tension and compression, and this is for heavy duty. It has 120 kips force. The previous one has 22 kips, but this one has a 120,000 pounds capability. This is another one with 22 kips. We got it as a donation from Aerospace Corporation. We use it for composites. These are some of my publications from theses. These are recent ones, 2019 and 2020 and 21. So this one is for a student, a Kuwaiti student called Abdullah Al-Sumait, and he did this work for MOOC, and we published it in the Journal of Materials Engineering and Performance. It has a impact factor of 1.8 plus. And this is another one for another international student. Her name is Karen Shen. She's now in Shanghai, China. And we did it for Weber Metals, and it was on fatigue as well. This one, Fahd Zubbi, and he is from Kuwait again, and he did his thesis on effect of grain size on fatigue. And again, notice it is in 2019. This one is for an American student, Alfredo Gutierrez. He works at Northrop Grumman, and he did his thesis on fracture toughness. And this thesis was sponsored by Northrop Grumman. And then in 2021, this month, we had another thesis published for a student called Sultan Al-Zubbi, and he's from Kuwait. And it was on the effect of trying to make magnesium a more ductile material. And there is a paper that we're writing now for another student. He finished his thesis in December 2020. And we're writing now the paper, and we're going to submit it also to a journal. And it is on 3D printing. It is on the effect of the layer orientation on the fatigue behavior of PLA samples. And these are some of the machines we're using for the theses. This is the 3 rotating beam fatigue tester. We're using also a lathe to machine the samples. I said that Sultan did in his thesis ductility of magnesium. He was using a rolling mill and furnaces and pencil testing. And currently, I have 3 students doing their MS theses with me, and it is on additive manufacturing. The first one, his name is Ivan Del Castello. His thesis is on the effect of thermal exposure on the mechanical properties of aluminum alloy, aluminum silicon 10 magnesium fabricated by laser powder bed fusion. And here we're looking at components which are manufactured by additive manufacturing to see how strong they will be after 100-hour operation, 500-hour operation, 1,000 hours operation, if they're going to stay intact or if they are going to lose strength. So the experimental work was done, and in December 2021, he defended his thesis, but now we're in the second draft of his thesis. We're looking at it, and if the 3 committee members, myself and 2 other professors, are happy with the draft, then he's going to graduate. And this work is sponsored by Boeing. The second thesis is sponsored by the JPL, Jet Propulsion Lab in NASA, and it is on the effect of something we call hipping, hot isostatic pressing, and annealing temperatures on tensile and fatigue properties of laser powder bed fusion titanium 6 aluminum 4 vanadium alloy. The student's name is Mark Sanga. He's in the middle of the experimental work, and hopefully he's going to graduate sometime at the end of summer. And the third thesis is really started a month back. The student, his name is Nick Osborne, and the thesis again is sponsored by Boeing Corporation, and it is checking on how we are producing additive manufacturing materials. We're trying to see if we can build it and then make it stronger before we put it in applications. So we're trying to do some heat treatments to make the material stronger, and we're going to check the microscopy, and the mechanical strength of different overaging treatments on it. So we're using in the theses furnaces. We have 6 of these furnaces. We have 11 ovens, and we have electro-discharge machining units. You know, if you have a lathe or any other classical milling machine, you produce debris, you know, powder, debris. This machine has a wire. If you program it, the wire will produce a discharge, and that discharge is going to cut the sample in a perfect dimension without a single drop of debris. So we have 2 of these machines. The first one, the old one, I got it from the National Science Foundation. The second one, the university was kind and they bought it for me. But we machine most of the critical samples on the electro-discharge machining unit. No debris, excellent precision, and we use it all the time. Also, we use a scanning electron microscope. Actually, this is in Life Science building across the street. Dr. Young John Lee, he operates the microscope, and he has the students learn it and use it. After you fraction a sample, you look at the surface to detect if the fraction was brittle or ductile or a mixed mode. Also, we use our optical microscope to check at the internal structure at 500 times magnification of different stages in the heat treatment, and the as built, and the as softened, as strengthened. So the optical microscope is a very important tool. And in the future, I have now a proposal from Boeing. They have 4 projects that they would like to do with us on additive manufacturing. And Aerospace Corporation, they submitted 3 projects that they would like to do with us on additive manufacturing. Additive manufacturing is a new concept. You know, before you used to like produce a block and cut it and drill holes and machine it until you make a component. These days, the additive manufacturing is you build the final product layer by layer by layer by layer by layer, and you don't need to, I mean, we call the old technology subtractive manufacturing and the new technology additive, because by going layer by layer, you introduce or you create the final product. So that's why we are, being hot on the subject lately. And the last thing is we're trying in the graduate program, hopefully by next fall, to add a certificate in additive manufacturing, a certificate in material science. So if you take 3 courses in additive manufacturing, other than your master's degree, you take a separate degree or a separate certificate saying that you took 3 courses in additive manufacturing and you have like a specialization in it, and the same for material science. And that's it, if you have any questions for me.
Thank you, Dr. Saeed. I really appreciate all that information. Maxwell, do you have any questions?
Yeah, I have one or a couple questions. With the additive manufacturing, I studied a lot of solar cell research in college, and I know they're working on something like additive manufacturing. They're layering the solar cells. Have you looked into any of that?
No, but I would like to get involved in that. You see, you can build a car by additive manufacturing, and you can build also a solar cell by additive manufacturing. So it is a new technique where you don't have to machine and to mill and to drill holes and to boil. I mean, it is a new technology, but it is still not fully studied. So that's why we're looking at the different aspects. Like now I see that the additive manufacturing as built is stronger than when you heat it or when you cool it or when you do things to it. So we're still learning. It's a new field, but it's going to be hot for many years to come. I mean, in my view, artificial intelligence and robots and additive manufacturing is going to be the hot subject for many years to come. So what you're saying, did I do that before? No, but I'm interested. If you find a company which will be interested in sponsoring us and do a thesis in that field, I would love to do it. Because unlike you, I have my background in physics. And I had to, when I went to materials engineering, I took like, I think 5, 6 courses in undergraduate, plus the graduate classes. So I had to also take remedial classes. But I understand what you're saying because I took the background that you have.
Yeah. Yeah, they use like different, they use additive manufacturing just because they used a lot of different materials when they make it to capture all the sunlight.
Sure.
Yeah. My other question is like how many like different fields of research are there? Because there wasn't a lot online about the different fields of research within ME. So I know there's yours, and what else is there?
Let's put it this way. We have people who are wonderful in thermal science. We have people who are wonderful in design and solid mechanics. So you see what area you want to specialize in or what thesis you want to work on. Then approach the professors. All of them have a PhD in their specializations. All of them have they did theses before. I did more because it happened that I've been here much longer than all of them. But whatever field you're interested in, as long as it is a thermal science or a solid mechanics, you will find one or more professors who will be able to get engaged with you, like bioengineering, like renewable energy, like thermodynamics. All these areas, we have them. If they're not put online as theses, if you have something that you're interested in, I am sure that I can find for you the right professor to connect with.
Okay. And since I'm coming from physics, I'm not quite sure what field I want to go into. Is it normal for like a master's student to like take a couple classes before they decide what professor to work with or what research to do?
Of course. And actually, we have a rule. I don't know if you read it in the website. If you come from physics or chemistry or metallurgical engineering or civil engineering or any type of other than non-mechanical engineering, you have to take 5 courses if you did not take them. One of them is dynamics. One of them is mechanics of materials, thermodynamics, heat transfer, and fluid mechanics. Yes, this is a long list, which will take you maybe a semester or even a semester in one course, but they will give you the background so that when you jump into the graduate classes, you're not going to feel a disadvantage.